1054, Chinese astronomers recorded a guest star, so bright it was visible in daylight for weeks. What they were watching was a star tearing itself apart, a supernova. Nearly 1,000 years later, the debris from that explosion is still expanding. We call it the Crab Nebula. Now, here's what we're going to do today. I pointed my Seestar at the crab, took a single image, and from that one image, using nothing but Python, we're going to measure how fast the debris is moving. Not an estimate, not a lookup, but really measure. We'll do real background subtraction, source detection, error propagation, the same methods professional astronomers use. And by the end, we'll have a number, kilometers per second, with proper error bars. Can this telescope actually do real science? Let's find out together. Every astronomical image starts as a FITS file. That's Flexible Image Transport System. Unlike a JPEG, FITS preserves the raw sensor data and includes metadata about how the image was captured. We are using Astropy to open the file. The fits.open function gives us access to both the pixel data and the header. That's where the scope stores information like pixel scale, coordinates, and exposure time. The Seestar captured this at 1.187 arc seconds per pixel. That number is critical. This is how we'll convert our pixel measurements into actual angular size on the sky. We've also got the WCS, or the World Coordinate System, data embedded in the header. This tells us exactly where in the sky we are pointing. Right ascension 83.7 degrees, declination 22.3 degrees. That's the Crab Nebula. Now that we've loaded our FITS file, we need to prepare the data for analysis. First, let's check what we are working with. Our raw data has shape 3, 3840 to 160. That's a three-dimensional array. FITS files can store color data in different orientations. Some put the color channel first, others put it last. Our Seestar image has the color axis first. That's the 3 for red, green, and blue. So for easier processing, we transpose the array so color becomes the last dimension. So now that you can see, it's last. Height, width, then color. For measuring the nebula's size, we don't need color information. We need to convert to grayscale by averaging the 3 color channels. This gives us a simple 2D image to work with. And here is something interesting. Look at these pixel statistics. Our values range from 23 to over 65,000. That huge standard deviation of 286 tells us we have bright objects against a dark background, and that's our nebula waiting to be measured. Before we measure anything, let's actually see our nebula. But here's the thing, astronomical images have enormous dynamic range, and how you stretch the data completely changes what you can see. So look at this. The full data range goes from 23 to over 65,000, but the display range, the first to 99.5th percentile, is only 28 to 60, so almost all our pixels are in that very narrow range. The bright values are just a few stars in the nebula core. So I did a linear stretch. It shows the data as is. You can see the nebula, but the faint outer structure is lost in the dark background. Then I did a square root stretch. It compresses the bright end and expands the faint end. Now we are starting to see more of the nebula's filamentary structure. The hot color map makes it a bit easier to see subtle variations. But for nebula, async stretch is often the best. It handles both the bright core and the faint wisps beautifully. This is what we'll use as our reference for understanding the nebula's extent. These aren't different images. They are the same data, just displayed differently. Choosing the right stretch is essential for both visuals and for deciding where the nebula ends and the sky begins. To measure the nebula, we first need to know what isn't the nebula. We need to characterize the background sky. And our strategy is simple. The Crab Nebula sits in the center of our image, so the corners should be mostly empty sky, and we'll sample from there. We take the outer 20% from each corner. That gives us 4 regions of 432 by 432 pixels each. Combined, that's nearly 750,000 pixels of pure sky background. Plenty of data for good statistics. We then use sigma clipping to reject any stars or artifacts that might be lurking in our corners. This iteratively removes outliers beyond 3 sigma until the statistics stabilize. And here, our background values: a mean of 31.15 ADU, median of 31, and critically, a standard deviation of just 2.24. That tiny scatter tells us our corners really are clean sky. Now, compare that to the full image statistics. The full image has a standard deviation of 286, over 100 times larger. That's the nebulous signal dominating the center. This background value of around 31 ADU becomes our reference point. Anything significantly above this signal is signal from the nebula. Next, we'll use this to define exactly where the nebula begins. Now we need to decide at what brightness level does the sky end and nebula begin. This is where sigma thresholds come in. We calculate multiple of them based on our background statistics. A 3 sigma means anything 3 standard deviations above the background median. That's, as we can see, 37.73 ADU. At 5 sigma, it's 42.21, and so on up to 10 sigma at 53.42. Think about what these numbers mean. Our background median is 31. A 3 sigma detection, the faintest we would actually trust, is only about 38 ADU. That's just 7 counts above the sky. But look at the dynamic range. Our brightest pixels hit 65,534. That's over 2,000 times brighter than the background. The Crab Nebula's pulsar and bright filaments are intense. The faint outer edges of the nebula probably live around 38 to 47 ADU, barely above the noise floor. This is why careful background subtraction matters so much. A few ADU of error could make the nebula appear 20 times larger or smaller. We'll use the 3 sigma threshold to capture the full extent of the nebula, including its faintest wisps. And let's visualize what we just calculated. Histograms tell the story of our data better than any single number, I think. On the left, here, we have our corner pixels, or the background. Look how tight the distribution is. Nearly all of the pixels cluster right around 31 ADU. The green dashed line marks our median. And you can see the 3 sigma and 5 sigma thresholds in red and orange. Almost nothing in the background exceeds these thresholds. And that's exactly what we want. Now the right panel shows the entire image on a log-log scale. This is where it gets interesting. See that massive peak on the left? That's still the background. Millions of sky pixels. But now look at the long tail stretching to the right, all the way out to 65,000 ADU. That tail is the Crab Nebula and the stars in our field. The orange 5 sigma line sits right where the background peak ends and the nebula tail begins. Everything to the right of that line is real astronomical signal. This is why log scale is essential for astronomical data. On a linear scale, the entire nebula tail would be invisible, crushed against the axis by the overwhelming number of background pixels. Here is where the real measurements begin. We are going to detect the nebula at 4 different threshold levels and see how our size measurement changes. We'll test 3 to 10 sigma. Lower thresholds capture fainter emissions but risk including noise, and higher ones are more conservative but might miss the outer edges. The detect sources function from phototils finds connected regions above our threshold. And the end pixels equals 50 parameter means a detection must have at least 50 connected pixels. This filters out cosmic rays and hot pixels. We create a catalog of all detected sources, then select the largest one by area. In our field, that's definitely the Crab Nebula. It dominates the image. For each detection, we measure the semi-major and semi-minor axes using 3 sigma extents. This captures about 99% of the source's light in Gaussian profile. We average these to get an effective diameter. Then we convert from pixels to arc seconds using our plate scale, and from arc seconds to arc minutes for easier comparison with the published values. Finally, we overlay an ellipse showing exactly what region we measured. The red dashed ellipse traces the 3 sigma boundary of the detected source. As we raise the detection threshold, our measured diameter shrinks. So as we can see here, at 3 sigma, we measured about 385 arc seconds. At 5 sigma, it drops to around 323, at 7 sigma, 280, and at 10 sigma, just 240 arc seconds. This makes perfect sense. Lower thresholds include the faint outer wisps of the nebula. Higher ones only capture the bright core. Neither is wrong. They are just measuring different things. The mean measurement is 307 arc seconds or about 5.1 arc minutes. The uncertainty is plus or minus 54 arc seconds. That's roughly an 18% uncertainty just from threshold choice alone. This is why you'll see different estimates for the Crab Nebula in very different papers. It's not that astronomers can't agree. It's that the nebula just doesn't have a sharp edge. Where you draw the boundary is a choice, and that choice affects all of your measurements. Alright, so anyone can measure something, as we saw. But maybe the real question is, how wrong are we? So first, the threshold choice, where we decide the nebula ends. That's 54 arc seconds of uncertainty, almost 18%. And honestly, that's not a failure of our method. The nebula genuinely doesn't have a hard edge. Then, pixel scale adds another 4%. Because our telescope's plate solution isn't perfect. And now, the Crab Nebula is roughly 6,500 light years away, give or take 500, That's 8% uncertainty baked into every physical measurement we will make. We can measure the angle precisely, but converting to actual kilometers, we are limited by how well we know the distance. The only thing we maybe know precisely is when this thing actually happened. 1054. The Chinese astronomers wrote it down. 0.5% uncertainty on nearly 1,000 years of expansion. So when someone asks how big is the Crab Nebula, the honest answer isn't actually a single number. It's a number, but with error bars. And those error bars tell us as much about the measurement as the number itself. So we've got two sources of angular error: measurement method and pixel scale. Now the question is, how can we combine them? Well, we can't just add errors. We need to add them in quadrature. Square each one, add the squares, take the square root. This actually comes from statistics. Variances add for independent variables, and standard deviation is the square root of the variance. Let's walk through it. 54.3 squared plus 12.9 squared gives us 3115.5. Square root of that is 55.8 arc seconds. So our angular diameter is 307 plus or minus 54 arc seconds. In arc minutes, that's 5.12 plus or minus 0.93. Here is the important thing to notice. If we had just added 54 plus 13 linearly, we would get 67 arc seconds of error. But quadrature gives us 56. The smaller error gets partially absorbed. And we get a relative error of 18% on our angular measurement. Actually, not bad for a backyard telescope measuring a 1,000-year-old explosion, don't you think? We've got an angular size. Now, let's turn that into something physical. Actual light years across. First, we convert to radians. 307 arc seconds become 0.00149 radians. Tiny number, but that's because the nebula only covers a small patch of sky. The small angle formula is beautifully simple. Physical size equals angle times distance. But it only works in radians. That's why we convert it. The Crab is 6,500 light years away, or about 2,000 parsecs if you prefer the professional units. Multiply 0.00149 radians by 6,500 light years and we get 9.68 light years across. Think about that. Light itself takes almost 10 years to cross this thing, and it's been expanding for 970 years. Now, the error propagation. For multiplication, relative errors add in quadrature. So 18% from our angle, 8% from distance, combined gives us about 20%, 9.68 plus or minus 1.91 light years. The distance uncertainty we talked about earlier, it's now baked into our answer, and we really can't escape it. Finally, we are almost at the end. So, we've measured the size, we know the age, now we can calculate how fast the debris is moving. First, we need a radius, not diameter. The explosion happened at the center, so debris traveled half the diameter to reach the edge, 4.84 light years. In kilometer, that's 4.6 times 10 to the 13th. The supernova exploded 970 years ago. In seconds, that's 3 times 10 to the 10th. Sounds like a lot, but cosmically it's really nothing. Now, velocity equals distance over time. We plug in the numbers and we get 1495 kilometers per second. And let me put that in perspective. 3 million miles an hour, or about 0.5% of the speed of light. This debris has been screaming through space at Mach 4,400 for 1,000 years, and it's still going. Our error is about 20%, almost entirely from the size measurement. And the time uncertainty, 0.5%. It actually contributes basically nothing. Thank the Chinese astronomers for that. And so there it is. From a single image taken with a Seestar, we've managed to measure the expansion velocity of a supernova remnant to within 300 kilometers per second. That's almost real astrophysics from our own backyards. If you want to take this further, and I really encourage you to try, image the crab. The nebula is still expanding. Or try the Orion Nebula or the Ring Nebula, whatever you've captured. Measure something, propagate the errors, see what you get, and let's compare. If this sparked your interest, I would appreciate a thumbs up. And hey, thank you for measuring a star explosion with me. See you next time.